Okay, good morning. So, optical coherence tomography today. I come from Canterbury. It's, as you go to London, the first major place before London. The fast train makes a stop in Ashford. So, if you want to visit Canterbury from Brussels or Paris, there is a stop close to us, with the TGV. And now we also have direct line to London via fast train, bullet Japanese train. And Canterbury became a commuting area. So from last year, many things changed in Canterbury. More and more people work and commute from work in London and commute from Canterbury. Come visit. You have a cathedral, similar size to what you have here. Don't be deceived by the weather. It's not always the way it shows. Like in all these adverts, inciting travelers to come and visit, they always put a blue sky. Not like here in Szeged. They don't need to put it this way. It's always blue sky. Fine. So these are the lines of the lecture. Let's not detail them for a while. There are three main pillars of the technology. They refer to sources, configurations, and signal processing. And I will have a little bit about each of them. Very simple. Very, very simple. I tried to, as I realized that there is a diversity of skills and fields here covering engineering, physics, chemistry, and medical clinicians. So OCT is mainly for health and has been developed to respond to an optical imaging need in medical applications. However, it has applications not only in health as well as in non-destructive testing, gas conservation. I will show you a little bit about that. The field is still strong. Every 3 years, the number of publications double. You can do these statistics. And another, the laser should be on the first one. Yes. Do I have a laser here? So the top one. The top one. Yes. So as you see, the statistic about the subjects is dominated by something to do with the eye. Retina, anterior, posterior, pole, cornea, ophthalmoscope. So more than 55% is eye imaging. If you look now at fields, this is old. The number is old. It's from 2014. The statistics, but it's still valid in terms of what are the fields dominating OCT. So that is the number of counts that you recognize at the top ophthalmology as well as cardiovascular. So I think last year when I was here, the laboratories have been shown applications in the eye and applications in the cardiovascular. These are the main two markets of medical imaging today, eye and heart. And as you will see from my presentation, there are some other directions which are now being advanced in research, and soon you will find commercial systems on the market to respond to those needs. So I place here a few arrows relevant for Lamelis, so the eye, surgery, as well as neuroscience, neurology, so they have been counts, pathology, and oncology. A big push in looking at cells and tissue connected to tumor investigations. That was a slide to give me some feedback about what are the skills of the audience. I think I'm already specialized for that after discussing with you last night. So there are, so hands up, how many here have heard about OCT? So right, you don't need any introduction. You don't need my lecture. How many have worked with interferometers? So interference is at the core of the basis of the optical coherence tomography. With lasers, okay, and medical applications, yeah, fine, easy. That was easy. So let me take this back. Do you know why OCT has been? What triggered development of OCT? What exactly? It has responded to a need. What was that need? What was that cause which pushed for this major technology to evolve and to be created? What was that need which justified the creation of technology? Do you remember from last year? Okay, so I need to do that again. Now, everything here will be about basics. So I have some novelties which I added to keep entertained those who came last year. Have some novelties. However, it's about basics of OCT. And the basics, like many technology and science, is the same. So you have to bear with me. If some of the slides you remember from last year, they are the same, but the basics are still the same. So that was the need. The need to image with good axial resolution, the eye. More on this. So until 1991, when OCT was invented, the technology, the high resolution technology for the eye was this: scanning laser ophthalmoscopy. How that works? Take a laser, very little beam splitter here. I'm not sure if you see it. It's a tiny beam which goes through cornea, yes, through the opening, the eye, and the beam practically pivots this point. Okay, so the eye lens will focus the light on the retina. Light will come back, will miss this tiny splitter, and it will be collected by a keyhole and a photodetector. So that is confocal microscopy applied to eye imaging. Now, everything about SLO, scanning laser ophthalmoscopy, OCT, everything is about resolutions. Resolutions which could be how well can we separate lateral pixels, how well we can separate axial. So let's investigate that. So what happens with a simple optical system like this? The eye opening is variable in between 2 millimeters in bright light to up to what is the maximum eye opening. How many miles?
10 to the minus 4.
Maximum 7, 8 millimeters, 7. So if you use a normal eye opening of 3 millimeter, you will get that blob. If you open the eye more, you see the blob becomes smaller. And there is an equation for that, and it's called in optics, this is limitation due to diffraction. It's called a disk, so you have a formula for that. So the larger the beam diameter, the smaller that one. So there is a way in which you can make that smaller by increasing the beam diameter. So better resolution would be, they are not bigger, not larger, but smaller. So when we refer to better, practical will mean smaller. I.e. you can separate two blobs which are closer to each other. So if you do that calculation, with 3 millimeters you can see the retina is 15 micron laterally, 15 microns. And there are many fundus cameras, SLOs on the market. If you look at their data sheet, it will be 15 micron, not better than that. If the eye is young, if the eye is that of a young body, the eye is good quality, less floaters in the pictures, good optics, and that would go to below 10 microns, but generally is even larger than 15 microns. If you go to 7 millimeter, you can practically reduce it to, theoretically, to a couple of microns, but this is not happens in reality. So even if you open it, you don't achieve that. I'll tell you more about that. But let's go now to the axial resolution. So if you keep the eye with normal opening, you don't want to drop anything to your eye to make it larger. Let's develop a technology which doesn't need anything to do to the eye. So we like to have a technology which will use the eye as it is, and that's what common ophthalmology practice does. Uses the OCT with no drops. So what is the axial resolution? If you look there in the confocal microscopy, you'll find that with 3 millimeter, and considering the focal length of, what is the focal length of the eye? How long? 2 centimeters. So if you consider 2 centimeters with an opening of 3 millimeters, you will find 200 microns. So you can separate in depth here points, layers, distanted by not less than 200 microns. If you increase the pupil, that would go to less than 50 microns. So instead of 200, you can go to 50 microns. So but what happens in practice? That's what happens in practice. When you open the eye, wider opening, what happens? The beam only extends over imperfections in the eye. So instead of going laterally over perfect lens, the periphery rays will see more and more from the aberrated part of the eye. So in this way, these rays here are not going to converge. So the spot is not going to be as nice as a regular globe. So because the spot is aberrated, both transversal and axial resolutions will suffer. So instead of nice globe, regular disc, you have a fuzzy shape. And with that one you cannot do it. So by working on the optics, there's not much you can do because the eye is fixed. You cannot adjust the focal length. You can only play with the opening. So, because that chance is gone, so instead of improving the focus, another idea emerged, that of using interference. And if you use interference and you do that interferometry with many wavelengths, the more and larger the color content of the spectrum, the better the axial resolution would be. And I'll come back to that. So you have it here, that these boundaries here, the boundaries of the optical source practically will determine less and less resolution in terms of how wide is that pixel along depth. So in this way, theoretically, even sub-micron resolution becomes available. And you realize immediately that with such a technology, we have done quite an important step in the fact that transversally, that 15 micron lateral resolution will still be there and determined by the optics of the eye, like these two parameters, transversal and axial resolution, they are all determined by the optics. You do a better focus, you improve both the transversal and axial. Here, the two parameters are shifted into two different directions. The transversal resolution is left to the optics of the eye, to the interface optics, to the optics like an instrument, while the axial resolution as a problem is being handed now to the optical source. And this technology got a nice acronym, OCT, invented at MIT. They had the idea to add a lateral scanner to a low coherence interferometer. And we've been doing OCT from 1993. And that was the first image produced at MIT. It was retinal tissue in vitro. And here in the central part where the fovea is, the thickness here is about 150 microns. Here we have something like 300 microns. Quite pixelated, but it was the first image and has shown already important structure in the eye. You can see layers already. And with the terminology of ultrasound, this is called a B-scan. A B-scan, like an ultrasound. And that's an image with better technology, developed by us by 2005, 2006. That was an instrument placed at the clinic in New York. And all technology in the hands of clinicians is now capable of deciphering all these layers here with very high resolution. And ophthalmologists and researchers in OCT would know what these acronyms means. Inner limiting membrane, nerve fiber layer, ganglion cell layer, inner plexiform layer, inner nuclear layer, outer plexiform layer, outer nuclear layer, external limiting membrane, ISOS. These are the terminations of the photoreceptors in the eye. And there is a lot of research here on the adaptive optics. RPE, the layer which fits with nutrients, the retinal pigment epithelium, and that's a field of tremendous research in this region, choriocapillaris. Many things happen here. So for age-related macular degeneration, the most important is this part, the central part of the eye, while in glaucoma, this is the part, because under the pressure, this layer becomes thinner and thinner, this nerve fiber layer. Now ophthalmologists measure this thickness with microns. So clinicians now have that fantastic metrology tool of following layers in the eye with no drops, safe, instant, to follow that thickness from visit to visit with micron resolution. And it's safe if you scan the beam. It's less than 1 milliwatt at 800 nanometer, and it's a technology now widely available. Now this is a school, so instead of bombarding you with all sorts of images and what we do in Kent, I wanted to clarify the technology for you. You go away and at least you have some basic notion of the technology, as well as clarifying all this clutter of terminology. So let's take it bit by bit. What is ABCD? So how many of these layers of knowledge you can describe? So how many letters here are known to you? B, like an ultrasound, yeah? B scan, okay? A is amplitude in electronics, in physics, but this also refers to a scanning protocol. It's one-dimensional scanning depth, like an ultrasound. The reflectivity profile in depth is called an A scan. You put several together, you get a B scan. What is a C scan? Constant depth scan, like in confocal microscope. You slice a layer behind the lens at a certain depth. This is constant depth. T is a Kent invention. It's not very popular because it comes from our group. It's practically, again, a one-dimensional scan, but not in depth, lateral. So if I move the beam laterally, what I collect will be a T-scan. If I kept it here, then you imagine that you have the layers under the red spot, that is the A-scan. Flying spot. Scanning laser ophthalmoscopy uses flying spot, i.e. the beam is flown over the target, flying spot. So generally when you use scanners, galvo scanners, resonance scanners, acoustic scanners, you will refer to flying spot. Full field. Okay. What? Full field would be like scanning with no scanning. It's like you use a 2D camera and you collect all the pixels in the image are illuminated at once. That's why it's full field. They are all illuminated at once. And the camera, you scan practically, you collect the electric charge from pixels, bit by bit. So instead of having a mechanical scanning which scans the beam, you practically scan the totality of charges coming along one wire in time. So you scan the charge on those pixels, XY pixels in the camera. So the process of mechanically flying the beam over the target is replaced in full field by scanning in time the charge on the CMOS or on the CCD camera. So generally, when you see full field, that means that you won't have one point flown over. You'll have all the pixels coming at once on the camera. But in fact, in electronics, there is still that element of scanning there. You don't see it, but it's there. Spectral domain, Fourier domain would be in the same category, is the modern OCT technology. The modern technology is based on spectral domain and Fourier domain. Time domain, the first image I have shown you, including the image I have shown you from Kent, they are based on the old technology, time domain. And I'll tell you more about that. Spectral domain and Fourier domain are the new technology. Low coherence interferometry, low coherence reflectometry is the field of evaluating the results of interferometry in an interferometer illuminated by a low coherence source. What is a low coherence source? A source which has a short coherence length. What is the coherence length? That's very difficult even for master students of optics to define the coherence length. I'll show you more about what is the interval. Swept source. This is the modern technology. All the technology now in OCT moves towards swept source. Swept is like you sweep the floor, clean it. Sweeping the wavelength. It's a tuning laser. Spectrometer, the majority of systems for the eye use spectrometers, which soon will be replaced by the other concept, sweeping the wavelengths. And mechanical scanning, back to the scanning. Why did I put that here while I have already been through A, B, C, D of scanning? Why do you think I came back to scanning? Because in the way OCT started with time domain. And in time domain, you scan the length of one arm in the interferometer mechanically. So by changing that, you practically do the A scan, which in Fourier and spectral domain is now replaced by the Fourier transformation. They don't need any mechanical means. Okay, so let's go through all this and clarify that today. This is a low coherence interferometer. So what do you spot here? You spot, let's say, the object under test, the eye. One, you see here the V splitter, light, going to the splitter, being divided into two, one to a reference mirror and one to the object under test, and the photodetector receiving light. So you may say that that is the configuration of a time domain. It's still the configuration for a swab source. And it has to be modified if you go to a spectrum interface. We'll go there. Now, this has the modern equivalent of this, where you take two pieces of fiber, you fuse them together, and you have any splitter here is like a 2x2, 2 inputs, 2 outputs device. It has 3 inputs, 2 outputs. The same here, 3 inputs, 2 outputs, 2 fiber put together. But it's easier to organize the optics by using fibers. So you see here after the light diverging from the fiber is now collimated by lenses, and that is an interferometer. If you don't use a laser and use a superluminescent diode, which has some broad spectrum, that will be a low coherence reflectometer or a low coherence interferometer. That's still not an OCT. What is missing here to be an OCT? What is missing? This is not an OCT. This is an interferometer illuminated by an optical source which has some bandwidth, has short coherence length, so that is a low coherence interferometer or reflectometer. What is missing? What do you need to add here to make it an OCT? What is OCT? The OCT creates an image that will give you only one point. So people at MIT added here a scan, repeated all the process for many lateral pixels, and that is now an optical coherence tomography. An essential slide which refers to the coherence length. So basics. These are very basic elements here. An optical source. You have one beam, and let's say that you use here a mirror to create a second beam and produce superposition of two waves. Now, I have deliberately shown here your wave train. The wave train is of this length. And if you look around us, like this is natural light. This natural light, that is that theory of Einstein, comes from spontaneous emissions. And these emissions take place fast. There are many such emissions, the excitations of atoms. And each day excitation process will take fractions of picoseconds to tens or hundreds of femtoseconds. So if you take that time and multiply by the speed of light, you will get the coherence length. So practically what the coherence length is, you can say that the phase here of the wave can be correlated with the phase up to this length. This length for natural light is 5 to 10 microns. It's no longer. However, if you take a laser, you can correlate to points along the wave trains which could be miles. Effectively miles. And that already shows the main principle of OCT, which is axial selection. You superpose these two wave trains, but the superposition will only create an interferometric effect as long as the delay of this wave train is less than the length of the wave train. So if you delay this, if I push this mirror down, this wave train will lag more and more behind, and there won't be any superposition. Of course, at the same time, there are many other such emissions. But the only interference takes place by superposing the wave train with itself. You cannot say, there are billions of other emissions, and I can do interference of this wave train with another one, which is already there. There are millions and billions. But that doesn't work that way, because the only wave trains which interfere are those which observe phase relations. If there's no phase relation, there won't be any interference. So it's only when the wave train interferes with itself. So this is not a pulse laser. It shows one wave train associated with that burst of emission from atoms. And more here, so you see this Michelson has the two arms equal. So when the wave trains return, boom, you have a constructive interference. let's do it again with a mismatch interferometer. So now one length is longer. So now, because one arm is longer, when the wave trains return, they will miss each other. So again, I would like you to understand it by doing simplifications. When we teach practically, simplifications create more problems. You may say, this is a pulse. No, it's not a pulse. It's one wave train. This is not a pulse. It's one wave train which I deliberately have shown it that short length to make my point. And depending on the coherence length, I would have made it longer. But similar to these wave trains, there are many other wave trains at the same time. But the only one which will interfere with will be its sister or brother. Only that will contribute to interference. And the mechanism is described here by object, wave, reference wave, and the interference is here. A square root of product of reflectivities. This is the correlation function. This factor takes into account the polarization of those two waves, and this is the fringe pattern. There are 4 laws of interference. There are 4 laws. Those who studied physics, optics will know those. Those who didn't, if you take any optics textbook, you will find those 4 laws. The first one is you can only interfere frequency with frequency at the same frequency. The second is polarization. You need to have polarization similar in those 2 waves. The third, constant phase. And the fourth is the most important for OCT, the most, is the delay. The delay of 2 waves interfering has to be shorter, smaller than the coherence length. That's the fourth law of interference. And for those with more engineering background, you have this association, which is this factor here. If you put more wavelengths into the spectrum, this factor, the Fourier transformation of this becomes narrow. So now if you go to the other extreme of a laser and you put all the colors in this light we see now, this will be very broad, but that will be very narrow and could become 1 micron here. So this fringe pattern will be multiplied by an existential factor for the duration of a couple of microns. Everything is about resolutions, so in terms of lateral, x, y, diffraction will determine the transversal resolution, this W. So the diffraction, the area, this size, while axially it will be the source, the coherence length. Okay. So please bear in mind this foci, the elementary 3D pixel. And let's follow the argument more on a Michelson. So you have a reference mirror here, another mirror here as object. This is a Michelson. And if you now look at the detector here, for each movement of the mirror by half wavelengths, the optical positive interference makes a wavelength. So the peak will go into the next peak, and so on, and so on, and so on, and so on. So if you use here a laser, this is what's going to happen. And this could go for kilometers, if that is a laser. You can move this by meters, kilometers, and you still obtain this. That's not a way to select in depth anything, because anywhere you put this mirror, you will still get peaks. However, if you replace this source with a low coherence source, let's say a source which has a, you can evaluate the coherence length here. How many peaks are? Let's say 6 plus 6, 12 times half wavelength. Let's say that the wavelength is 1 micron. 12 times half micron, 6 micron. So this is an optical source which will have a coherence length of 6 micron. So now, if I move this mirror 6 micron away, it will be outside this fringe pattern. And that's the principle of coherence gating, which any OCT would employ. Is that clear? How the axial resolution is based on this? because the tissue is made here by several layers. So to get the signal, I have to move the reference to the length of the layer 1. If the layer is here, this length is longer, so to get another interference pattern, I have to move the mirror here. So by moving this mirror up, I can practically select interference from different layers. And the capability of this device now, as this is shown, is practically 6 microns. Okay? If I wanted to make 3 microns, what do I have to do? If I wanted 3 microns. If I wanted 1 micron, what shall I do? What shall I modify?
The spectrum of the source.
The spectrum. If that was 6, I should put the content spectrum twice wider. Make it wider by a factor of 2. More here, let's say that take a glass plate. The glass plate will have a discontinuity between air, glass, air. So this sigma 1, sigma 2 will be the surfaces of the glass plate between 2 indices of diffraction, air, glass, air. So as you move the reference mirror up, you will go over the fringe pattern, those 12 peaks. Here you have 1 millimeter, so there will be a gap. I still move the reference mirror, and after I moved it about, if the glass plate was 1 millimeter, how much shall I move it from here to here? So the glass plate is 1 millimeter. How much shall I move the reference mirror to match now this interface? If the glass plate was 1 millimeter, how much shall I move it?
980 microns. I feel 1 millimeters and the
So the glass plate is glass and has a thickness of 1 millimeter. How much shall I move the reference mirror?
1 millimeter to go to the center.
So I refer to this. I put here a glass plate, there are 2 layers, and in between them I have 1 millimeter of glass. How much shall I move this reference mirror to match, to get this for this surface, and now I wanted to get the same but for this surface. How much shall I move it?
Twice.
No, because this goes round. So it's 1 millimeter times the index of refraction of glass. So it's 1.5. So if I move the reference mirror by 1.5, I will get this 1. Okay? Fine. And there is something else here. Depending on the velocity I move the mirror, practically I scroll in time. I experience this modulation. So I go in time through this. If I move the reference mirror faster, I will have in time a generation of an AC signal, alternative current. AC signal, which is faster and faster depending on how fast I move that mirror. And this is nothing else than this frequency. The fact that you have a moving mirror, and the moving mirror reflects light back is a shifted spectrum. And the shift in the spectrum is practically the Doppler frequency. And the Doppler frequency is 2 over lambda, because it's 1 v over lambda and the ray is reflected back. So that's why you have a factor of 2. So if you move the mirror at 1 millimeter per second and the wavelength is 1 micron, this is 1,000 times 2 kilohertz. So by simply moving the reference mirror, you transform your interferometer into a RF generator. You move a mirror and the photodetector will deliver 2 kilohertz. So now you place a bandpass filter, okay, and get the 2 kilohertz. Use a rectifier. You know what a rectifier is? Yeah, you wanted to eliminate, to put these peaks up like any power supply. Every device uses DC, while at the mains, the plus and minus changes how many times? How many times the plus and minus change at the plug, at the mains? How many times a second? How many times? Can you put your iPhone into the mains? What happens if you put it in the mains? You'll blow it up. Why? 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 So what this device which you have in between the laptop and the mains will do? Between the power supply and the laptop. What does it do?
Removes the oscillation.
What does it mean to remove the oscillation? It does more than removing the oscillation. What does it do? How many many times the plus and minus changes place in Europe, how many times a second in Japan, and how many times in the States? When you buy an adapter from the airport, you have to know that. What you check on the adapter on the airport? You look at it and see what? Voltage is one, but more important is something else. What? Frequency. So here the plus and minus change their places 50 times per second, 50 Hertz. In States, Japan, 60 times per second. And some devices may not work. You have to make sure that they are universally acceptable, 50 Hertz, 60 Hertz. So what that little adapter will do, will practically take these oscillations, put them up, so you have now only positive, and you add an extra low-pass filter, and you obtain this under. Because you cannot use this. What you are not interested in picks ups and down. But the mains you have picks up and down. If you put those ups and down in the laptop, you will kill it. All these electronics is all made to accept at a wire plus and at another wire minus. If you change this, you confuse it forever. You need to apply plus to the plus label and minus to the minus label. And that device does this process which is called rectification.